An internal combustion engine is a machine of contained violence. Inside the block, pistons fire thousands of times per minute, spinning a crankshaft at speeds that would tear standard metal apart. But the drive wheels of a vehicle require something different: slow, deliberate, high-torque rotation to overcome the static inertia of a 2-ton mass. This creates a physical mismatch. Gasoline engines generate their peak torque and maximum horsepower within a narrow window of rotational speed, known as the power band. If you directly couple that spinning crankshaft to the drive wheels, the system would fail. At a dead stop, the load of the wheels would force the engine to stall. Even if you could get moving, the car will have no off-the-line acceleration and reach top speed almost immediately, hitting the engine red line before merging into traffic. The transmission functions as a dynamic mechanical interface and torque multiplier. It decouples the engine's speed from the wheel's rotation, allowing the motor to work efficiently regardless of the vehicle's velocity. The transmission exists to solve a physics problem, manipulating torque and speed under continuous load, to prevent engine failure while maintaining the machinery in its optimal power band. In automatic systems, the first step to solving this problem is removing the direct mechanical link. This is achieved using a fluid buffer known as the torque converter, which allows the engine to idle while the vehicle's wheels remain stationary. This cutaway illustrates the interior of a torque converter housing. The engine spins the red impeller, driving hydraulic fluid outward with kinetic force. This fluid strikes the turbine blades, forcing the input shaft to rotate. The central stator then redirects returning fluid to multiply torque. While fluid coupling prevents the engine from stalling, it introduces parasitic thermal losses. Pushing liquid to transmit power is less efficient than a locked, direct mechanical connection. The manual transmission relies on a different architecture. Its design centers on the spatial translation of power across parallel sets of gears using physical lockup mechanisms. This wireframe displays the layout of parallel shafts inside a manual gearbox. Power flows from the input shaft down to the lay shaft, seen here in red. Because they are constructed as a single unit, all gears on the lay shaft spin together. Notice the blue gears on the main output shaft. In a manual transmission, all gear teeth are meshed at all times, but these main shaft gears are not yet turning the output shaft. They freewheel on their bearings, spinning independently of the shaft they sit on. To change gear ratios and drive the wheels, the system must temporarily remove the rotational load from the engine. This requires a physical clutch. Pressing the clutch pedal pulls the pressure plate away from the amber friction disc and the steel flywheel. This breaks the physical connection, allowing the driver to select a new gear without the components being under load. With the load removed, the driver moves the gear shifter. This pushes a rod connected to a shift fork, which slides a splined collar horizontally along the main shaft toward the chosen gear. The sound of grinding gears is not actually the gear teeth mismeshing. It is the sound of the dog teeth on the outside of this collar failing to slot into the holes on the side of the gear, because the two components are spinning at different speeds. To prevent this, modern cars use synchronizers. The synchronizer uses cone friction to match the rotational speed of the freewheeling gear to the collar before the dog teeth engage. Once speeds are matched, the collar locks into the gear. Power now flows from the lay shaft through the locked gear into the splined collar, and finally out through the main shaft to the drive wheels. Manual transmissions achieve high mechanical efficiency through this direct physical lockup, but they require a decoupling of power to change ratios. Every shift necessitates a momentary interruption in torque. Traditional automatic transmissions replace parallel shafts with concentric epicyclic gear sets. These planetary gears manipulate ratios without moving components along a shaft. A planetary gear set consists of 3 components. In the center is the amber sun gear. Orbiting it are the cyan planet gears and their carrier, and encompassing the entire set is the steel gray ring gear. These gears remain constantly meshed, fixed in a single 2-dimensional plane. This removes the need for the sliding collars and shift forks found in a manual gearbox. Instead of sliding gears, ratios are changed by holding one component stationary while driving another. In first gear, the engine drives the small sun gear. A brake band clamps down to hold the planet carrier stationary. This forces the outer ring gear to rotate, providing a slower output with increased torque. For overdrive, the input drives the planet carrier, while the band locks the sun gear. This forces the ring gear to spin faster than the input shaft, allowing the vehicle to maintain high speeds at lower engine RPMs. The behavior of these sets is a mathematical function of the number of teeth on the sun gear versus the ring gear. Changing which part is held stationary determines the resulting gear ratio. In a physical transmission, hydraulic fluid pressure is routed to actuate multi-plate clutches and steel bands. These act as the holding mechanisms that shift the gear ratios. The epicyclic architecture provides a constant flow of power without shifting gear locations, but requires intricate hydraulic routing and precise control of the holding mechanisms. Automotive engineering is defined by a stalemate between these two layouts. The manual offers high efficiency, but suffers from the torque interrupt. This matrix chart shows the trade-off. A manual removes load to shift, creating a momentary drop in power to the wheels, a shift shock. Traditional automatics use hydraulic switching for continuous power, resulting in a smooth torque line, but with a penalty. The torque converter's fluid coupling creates parasitic efficiency losses. The engine must work harder to move the vehicle compared to a direct mechanical link. This dilemma was addressed in Group C endurance racing. In the Porsche 962, engineers needed the efficiency of a manual, but could not afford the milliseconds lost to torque interrupts during gear changes. Overcoming this dichotomy required moving past iterative improvements to traditional layouts. Engineers developed a different kinematic architecture by synthesizing the strengths of both systems. The result was the dual-clutch transmission, or DCT, a mechanical synthesis of the manual and automatic paradigms. A DCT nests two separate manual gearboxes. The odd gears, first, third, and fifth, mount on a solid inner shaft. The even gears sit on a hollow outer shaft. Two independent, computer-controlled clutches are used. One manages the odd gears, the other controls the even gears. This allows for pre-selection. While accelerating in first gear, the computer engages second gear on the freewheeling outer shaft. The shift takes 8 milliseconds. The odd clutch releases, the even clutch clamps down, handing off torque without dropping speed. This achieves a 1-to-1 mechanical lockup, removing the parasitic loss associated with a fluid torque converter. It simultaneously delivers the continuous power flow of an automatic. As the matrix chart shows, the torque delivery remains flat, providing the driver with uninterrupted acceleration. A transmission's architecture is defined by how it manages the trade-offs between mechanical simplicity, thermal loss, and kinetic output. By eliminating the compromises of fluid couplings and manual torque interrupts, the DCT provides the highest degree of mechanical optimization in modern power delivery.